Assalamu alaikum dear students. Today we are going to discuss about the logic circuit experiment number 5. Okay, the experiment is about asynchronous binary up counter. Now, what is binary up counter? The binary up counter, we can say that this is a sequential logic circuit which is going to do the binary number counting from minimum to higher value. Normally, it will start from 0 and on each clock pulse it is going to increment by 1 up till the maximum value we can have, like 0, 1, 2, 3, and up till so on. Secondly, we have asynchronous counter here. We say that it's asynchronous because the clock input of all the flip-flops within a counter does not take a common clock signal. Like each clock's input is going to take a different clock signal here. So let's start first with the discussion about what is a counter and how it is going to work. First of all, for the binary up counter or even all the basic counter, we are going to use the flip-flop which is going to give us the complement state here. The flip-flops which you have studied already in your theory and even in the last lab, we know that we have basically two flip-flops which are going to give me the complement state here. For example, we have T flip-flop. Whenever the input T is equal to 1, the output will be the complement of your previous state here, of the complement of the current state, in fact, basically. Okay. Similarly, we can use a JK flip-flop. In case of JK flip-flop, we say that when the input J and K are equal to 1, it will complement your current state here on the next clock edge. Okay, so basically I have constructed the binary up counter, which is basically 2-bit binary up counter, because I have used the two flip-flops here. And what we did, the T inputs of both the counters we have connected together and has given the logic one here, means it will be always high here. So it means whenever we have a clock transition coming here, depending upon the high input, it is going to complement whatever the current state it has. Now, second thing here, if you see here, we have a clock signal. And if you see with the clock input, I have a bubble here with the flip-flop. It means these flip-flops or this counter is going to trigger on the negative edge of the clock here. Okay. So let's have a timing variable. I mean, the output will be Q0 and Q1 here. Okay. Now, let's suppose this is your original clock signal here, the main clock which we are given to the flip-flop here. Just one more thing, I think I forget to tell you, like we call this one asynchronous because this clock signal and this clock signals are not taken from a common clock here. It is taking a clock signal from here, whereas the second flip-flop is taking the clock signal from the output of the first flip-flop here. So it means we don't have a common clock signal, so it means it is asynchronous. If all the flip-flops takes the common clock signal, it means we will say that they are working on the same clock and it is asynchronous counter here. Okay, but right now we are discussing only about the asynchronous here. Now what we have in the clock signal, you can see I have marked the negative edge of the clocks here. The negative edge means there is a transition from 1 up to 0 here. Okay, we can also call it as the falling edge of the clock here. Okay, now all the decisions the flip-flop is going to make on these negative edges here. So to start with, initially what we will do here, we say that we will reset both flip-flops here. So reset flip-flops or reset the counter means I'm going to have 0 0 initially in my flip-flops here. So initially all the values will be 0 here. So if you see here, till the first negative edge of the clock here, till the next first negative edge of the clock here, the input Q0 is 0 and similarly the output Q0 and the Q1, both of them are 0. So what will happen when this 0 comes at the first negative edge of the clock here? It will see that the input for the first flip-flop is high. So if the input is high, it means it is going to complement your current state. The current state here is reset, so it will complement and make it set here. And this set will remain the same value until the next negative edge of the clock here. On the next negative edge of the clock, again the flip-flop will check the value of t, which is obviously high here, so it means it will complement again, so it means it will change from set to reset state here. So simple is the Q0 is going to perform the complement state on each negative edge of the clock. It means the Q0 is going to toggle on each negative edge of the clock. So I will have always is waveform like this for Q0 here. Okay, let's discuss about the Q1 here. For the Q1, again, the output or the input here is high, so it means always it will complement depending upon this clock signal here. Now you can see this is a negative edge of Q0, so it means we have marked Q0. We say that for Q0 here, this is the negative edge, this is the negative here. So this output will depend upon these transitions here. So initially it was reset, so it will be reset until the first negative edge of Q0 here. At the first negative of Q0, when it see here, it's find that okay, the value of t is 1, it will complement again. So the value will complement from 0 to 1 and it will remain the same value until the next negative edge. On the next negative edge, again the value will be complemented from the set to reset here. So I got this waveform. Okay, it will keep the same pattern till infinity here. Okay, now for the two flip-flops, how we say okay, this is doing the counting. Okay, we got a waveform which was simple from the given diagram here, but how we say this is counting here. So for counting, what we will do here, one minute. For the counting, what we have here, if you see, this is a table. My least significant bit will be Q0. Then I will have Q1, and if I have another flip-flop here, it will be Q2, which will come here, and so on here. So initially what we have, you can see here, this is the value 0. So for the first time, Q0 and Q1 are 0, 0 here, so which Q0 and Q1 are 0, 0, and the decimal value is 1 here. For the next time, the Q0 is 1 and Q1 is 0. So Q0 is 1, Q1 is 0, which is basically 1 in decimal here. Similarly, it will become 1, 0, which is 2, and 1, 1, which is 3 here. And it will again repeat the same pattern here. Now, the question is, why it is repeating the same pattern after 3 here? Why it is coming back here? Simple. How many flip-flops we have? We have 2 flip-flops here. So, the total number of counting it is going to perform is 2n here. 2n, okay. So, it means 2 power 2. 2 power 2 means it will become 4. So it will only count the 4 numbers here. Means starting from 0 up till 3 here. Okay, and then it will repeat again. If I have another flip-flop, for example, if I have another flip-flop here, for example here, what will happen? The eraser, okay. For example, I have another flip-flop here. Okay, this is the clock input here again at the negative edge of the clock. Okay, and this is again high here. The output Q3, Q2 maybe. What will happen? Simple. Q2 will be, it will depend upon the negative edge here. So it will be initially 0 here, then it will become 1 here, and so on. Okay, and if you put it here like 0, 0, 0, 0, then 1, 1, 1, 1. So it will become 4, 5, up till 7 here. Then it will repeat again. Okay, so depending upon the number of flip-flop, it is going to continue here. Okay, I hope it's clear now. So this is the waveform we are going to discuss today, or in fact in the experiment we are going to see this waveform. Okay, in the experiment basically we have 4 flip-flop. I will only show the result till 3 o'clock. Fourth one is similar, I mean. So let's move here now. Let's move to, okay, let's move to next slide. Now this is the connection diagram. Okay, as per your manual here, it's given to you. So I just make the same connections here. I mean, maybe it's clear. Just go through it. It's exactly the same. Means all the connection clips we have connected here. According to the manual, he said that connect this input A1 with the +5 here. So I have connected this one with the +5 here. Secondly, this one here, this input, I think A2 maybe. Okay, this input is connected with the switch, and I have connected with the switch as per the manual here. And in B1 here, B1, I'm going to give a clock signal here. Okay, so first, before going the clock signal, I need to adjust the clock here. Okay, I just connected just to show you the diagram here. So please go through it and we can discuss in the lab session if you have any doubt. Now, according to the manual, what we need to do, we need to give a clock signal which is 1 kilohertz here. So how we will do? This is the clock generator here, okay? This one. So I just use a clock generator here. I give it as 1 kilo because I need 1 kilohertz clock signal, and I made the frequency equal to maximum. So hopefully it is going to give me 1 kilohertz of pulse waveform or the square waveform here. Okay. Now, just to check, is it 1 kilohertz or no? I just connected the clock signal, means the positive I have connected with the probe here, and the ground I have connected with the black of the probe here. Okay, I want to see the waveform on the oscilloscope here. Okay, so I have connected the first channel 1 of the oscilloscope with the clock generated output here. So if you see here in the channel 1, you know how to operate the oscilloscope because you should have studied this thing in the testing one. Just to show you, this is the waveform I got here. Okay, now if you want to measure what is the time period here, okay, what is the frequency here? So obviously I cannot measure the frequency directly here, rather I will find a time period here. After finding the time period, I can find the reciprocal of it, and I can get the frequency here basically of the time period. So what we have here, this is one time period, and obviously I think it will take one box here, okay, most probably. So this one box multiply by my time scale, which is 1 millisecond here. So 1 millisecond is my time period here, and the frequency will be equal to 1 divided by 1 millisecond, which is 1 kilohertz, which is shown here. Okay, delta t is 1 millisecond basically. That's why I get 1 kilohertz signal here. So it means the input which is we are given is basically 1 kilohertz here. Next thing is, now we will connect the same clock after making it 1 kilohertz to the input here. Okay, so we have connected it and given to the inputs here, input B here, and just to check the output, you can see the output of the first flip-flop. I think I have connected the second flip, just to show you. This is the output of the second flip-flop. I have connected the common here, and I have connected with the channel 2 of the oscilloscope here. Okay, so if you see here, for the first flip-flop, when I see the output, like I make the input upward, which is basically my clock signal, I made the first flip-flop output here. So you can just only verify here. You can see here the one cycle, one time period of the clock. In fact, okay, one time period for the output F1 or maybe the Q0 is equal to the 2 time periods here, roughly. Okay, not exactly. I think it's a bit shifted version here. But so the 2 cycles is equal to 1 cycle here. Okay, this is what we already calculated previously in the timing waveform here. Next one is, if I go to the next one, so you can see here for the output here, I need 4 for 1 cycle of Q2, I need 4 cycles of my clock signal here, which you can verify here. So this is all about today's experiment here. Okay, thank you. Assalamu alaikum.